Hello everyone. In today's lecture, we'll be discussing how we can design multi-input control law algorithm. This is very important in modern control techniques. As of now, you have deals with the single input, but if the system has multiple input to control the state of the system, how can deal with this kind of problem? And also, we'll have the lateral stability augmentation system. So we'll use this multi-input control algorithm concept and how we can apply that concept to design the stability augmentation system for the lateral motion of the aircraft. So here, let's assume we have a second order system, x1 dot, x2 dot, and we have the matrix A1, A2, A3, A4, the system matrix, and I have state vector, and we have the control matrix B, for example, and we have two inputs, E1 and E2. Okay, so here the dimension of the B also we can write. Okay, instead of that we can write maybe the control matrix B1, B2, B3, and B4. And if you notice here carefully, we are having two control input, E1, E2. But in the previous example, whatever the system we have taken, we had only one control input. So how to deal this kind of problem? So here, if you write in state space from the system, we can write x dot equal to ax plus bu. So here u is actually u1 and u1 and u2. So there's a scientist, Oman and Shudat, Oman and Shudat proposed method where we can design multi-input control algorithms for the system. So the control algorithm can be defined as, for this multi-input system, U equal to minus G K transpose X plus UP. So here you can write where G is very important parameter here, constant matrix, and K is the gain vector, and UP is the pilot control inputs. Pilots control input. So before you push it, if you would like to design this U1, U2, so for that we need to have control matrix for this design. If you want to design U1, U2, we should have the control gain matrix K1, K2, K3, and K4. And we have X1, X2. In the previous case, if you remember, if you want to consider only U1, so we had K1, K2, and X1, X2, right? This is how we have designed. But in this case, we are going to design two control inputs separately. So that our control gain matrix should be in the structure. But the system is second order system, but we need to find four defined control parameters. So it is quite challenging. Four unknowns, and if we have system 2 cross 2. So this is to avoid this problem, our control algorithm has been modified in the structure, where Z is assumed to be row vector and Kt is the control matrix. So now if you substitute this, okay, let me define. This is equation 1 and this is equation 2. Substituting equation 2 in equation 1, we are having x dot equal to ax plus b into minus j 18 x plus up. Or we can write ax minus bj A transpose x plus b up. Right. And from this we have the augmented matrix A minus b g kt k transpose into x plus b up. So here we can write ACL, a closed loop control matrix or system matrix. We can write A minus BG. Okay, in this equation we can write ACL x plus B UP, where ACL BG A transpose. So now the question is, how we'll choose this Z? This is very important. So G, generally as a design and control design engineer, we choose, suppose G is the row vector, or for the second order system, we can form G as G1, G2, G1, G2. So for this, we have to choose G1 or G2 is equal to 1. And what we're going to do is we'll use this condition, and from this we can find if G1 is, for example, 1, so we can form some ratio G1 by G2 equal to U1 by U2. And from this, we can find G2 equal to U2 by U1. This is how we can define. And we'll have example how to build this problem just now. So this is how we'll be choosing G. So basically in our problem, G1, G2 is known to us. We'll assume some values, and based on that, we can, in that case, if you notice carefully, suppose G1, G2 into, we have, sorry, we have to write like this. If G1 is, so basically we are finding GKT equal to, we can write G1, G2 into K1, K2, and here we can write G1, K1, G1, K2, G2, K1, and G2, K2. So this is basically, if you notice in this matrix, we have G1, G2 is known, sorry, G1 and G2 is known, and K1, K2 are unknown. So only two parameters unknown. The same way, I mean, if we apply this concept, we can convert the system into the simple form what you have done before. So let's take an example. This part will be clear. So example, design lateral stability augmentation system to improve the Dutch roll. So Dutch roll, one of the approximation in lateral stability. This part already we have done in our last course, so I'm not going to repeat the Dutch roll motion. Dutch roll characteristic of an aircraft as, so here we are having two parameters, two state variable, del beta dot and del r. And second order system we are considering Dutch roll minus 0.04, minus 0.99, 1.5, minus 0.21, and we have the state variable delta beta and delta r. Plus we have the control matrix 0, 0.03, 0.01, minus 0.008, and minus 0.08. And we have the control input delta del A, aileron, and delta del R, radar. Okay. So if you notice in this equation, we are having two control input. One is del A, and this is radar input. And the DJR handling characteristic are given by damping ratio is 0.3 and natural frequency is 1 radian per second. So using these parameters, we can form the DJR characteristic equation, and we can tally the augmented characteristic equation and the DJR characteristic equation, and we can find the unknown parameters K1, K2. So let's start the problem. So we'll be using this concept, what you have done in this page. We'll use this concept, how we can find the multi-input controller algorithm solution. So here U is, we can define as del delta A and delta del R. Okay. And G we are defining as G1 and G2. And K, K1, K2. And X is the state vector delta B and delta R. Okay. Now we have to construct and see. Here actually basically we can say G actually relates the authority, sorry, the control authority between aileron and radar. And you can say for augmentation. So we are assuming similar to the explanation we had here. So we are assuming G1 equal to 1 and G2 we can find we are assuming 0.25 some parameter value we are assuming equal to delta R and delta A. So this is the value we are assuming, some value, and this is our assumption. So we can write with this assumption, let me write here, so these are the things you have to assume as a control engineer. You have to choose these values and you have to see the result, whether you are able to track the desired values or not, and how can you improve the system performance. So this is basically, you can say, trial and error in some sort of. So with this assumption, maximum operating of radar and LRM would be achieved. So now we'll find the augmented matrix ACL equal to A minus BG A transpose. This is we had before here. This is the augmented matrix. So here we can write A minus B star KT. So A transpose. So here B star nothing but BG. So here, if you notice carefully, this system has been converted to simple augmented system, what you had before, BKT, simple. So here, we're gonna find this value. So first we'll find, okay, one more thing. Here we are going to use Bas-Gura method. Bas-Gura method. What you have done in the previous lecture to design the control. To design the control. Yeah, and so now first let's find the B star. So B star, we can find BG equal to, so B matrix given to us 0, 0.012, minus 0.008, and minus 0.08. And into G vector is given to us, so G is 1, 0.25. So from this, B star is obtained to be 0.003 and minus 0.028. And also we are given the desired characteristic of the desired dynamics. So zeta is 0.3, damping is 0.3, and natural frequency 1 radian per second. So from these values, we can find the desired characteristic equation. So desired characteristic equation we can form S squared plus 2 zeta omega ns plus omega n square equal to 0. And if you substitute the damping ratio and natural frequency, so we'll have the equation S squared plus 0.6 S plus 1 equal to 0. So this equation also you can represent in terms of alpha, what you have done before during the Bas-Gura method. So you can write S squared plus alpha 1s plus alpha 2 equal to 0. So here alpha vector we can define as alpha 1, alpha 2, and which is alpha equal to 0.6 and 1. Right. Now we have to find the A vector also of the system polynomial. So that we can find now A vector, because in Bhaskara method, if you remember, we had alpha A and also P and W, right? So these are the parameters we had. Yeah, this is the expression we had for the Bhaskara method, right? The K, how to find the K matrix of the Bayesian control gain matrix. So now A vector can be obtained from the Plant matrix A, right? So for that we have to find the characteristic equation is 0, 0 is minus the system matrix 0, 0.0, sorry, 0, 4, 4, 9, 0, 0.09, sorry, 99, 1.5 and minus 0.21. So equal to 0. So I have missed one term here. It will be 4 9. Okay. This is a matrix. And from this, we have the characteristic equation. The determinant of this matrix is obtained to be S plus 0.04 into S plus 0.21 plus 1.495 equal to 0. Or we can have S squared plus 0.25 S plus 1.5 equal to 0. Or this equation we can write S squared plus A1S plus A2 equal to 0. And A vector we can find A1, A2, which is 0.25 and 1.5. Now we have to find the P matrix, the controlled matrix. So we have to use this B matrix here, this B matrix. Instead of simple B, you have to use B star matrix. So here, the contributed test matrix is P equal to, we can write B star, A, B star. Or we can write B star is, so from this we can find minus 0.049 minus 0.99, 1.5 and minus 0.21. Sorry, here at A, B star, this term we are finding here, into B star already have 0.003 minus 0.028, right? And this found to be 0.02, 0.01. And so P can be found, B star already found, so we can put A star here, 0.003 minus 0.028 and AB star 0.02 and 0.01. Right. Now we have already A1, A2. This A1, A2 we have. So we can also find the W in the Bhaskara method. Yeah. So W can be formed as 1, A1, 0, 1. How to form W, that is already we have discussed. So we have 1 here, 0.25 and 0, 1. And simply you can use the formula K equal to PW transpose whole inverse alpha minus A. Right. And solving this, K found to be minus 60 minus 13.7. And we can find the control algorithm is found to be U equal to minus G K transpose X. And this control actually nothing but our del delta A del R. Right, this U actually. And so here also we can write equal to minus G1 G2 into K1 K2, and we have the state vector delta del beta and del R. And if you find the equation form, so del delta A, we can write minus G1 K1 delta beta minus G1 K2 delta R, and delta R equal to minus G2 K1 del beta and G2 K2 del R. So these are the control algorithms for this system. If you notice, this control is two controls are there, right? Two controls. So now this is how we can find our control gain parameter. Now, if you want to use different formula, you can easily use. Instead of Vascular method, you can use different concept how to solve this problem. You can use the place command, all this stuff. So there's another way also you can find the system, because linear dynamics is given. You can find the okay, if you want to use another method, let me give you the hints. Another method. To find control parameters. So here you want to use basically ACL found to be A minus B G K transpose, and from this you can find the closed loop characteristic equation. So basically we can find ASI minus ACL equal to 0. So I is basically 2 cross 2 identity matrix. So we can have ASI minus A plus BG A transpose equal to 0. And if you solve this equation, we'll have G already we have found S square plus 0.25 plus 0.003 K1. I'm not going through the whole steps. So K1 minus 0.02 K2 into S plus 1.5 plus 0.2, sorry, 0.02 K1 minus So plus 0.003 Q2 equal to 0. And also we have the desired dynamics, desired characteristic equation. We have x squared plus 0.6 s plus 1 equal to 0. So if you compare both this equation, so k found to be minus 16 and minus 14.7. This is the control vector. You can control gain matrix. You can find. So if you notice here, the k found by this method and k found by this method are same. So now we can go to the MATLAB code, how we can solve this problem in MATLAB. So this is the MATLAB code for this problem. So if you notice, we have this is basically here actually we have different. So we have done for the beta, and dotted line is the basic air plan, and down the solid line basically gain matrix and gain vector. So if you notice here, we can see that the system goes to 0 equilibrium point, and this is the whole code what we have done here. The same thing we have done in the MATLAB. So you can go through the details. You can try in your MATLAB command window, and we're supposed to get this result. I'm not going through the details. This is same, the A matrix is given, C matrix given. So C matrix, we are assuming all states are available in the output, and D is 0. So this is how we can, this is a closed loop system, and initial condition assumed to be 5 degree. It is 5, and this 5 radian, and this is the closed loop system, and you have the initial command to find the solution of the closed loop system equation, and this is basically how to plot the states. So you can try in MATLAB and you can have a result. So let's stop it here. We'll continue in the next lecture how we can design a stability augmentation system for the full lateral motion dynamics of the aircraft, and also we'll be assuming multi-input conditions. Thank you.